So in previous class we discussed on stationary distribution. So what is stationary distribution? We give an example of shuffling of cards. So we know there are 52 cards, and after some deal or after some game, the cards may not be in random. Basically, it's not in random. Some pattern are there. Some suits are in consecutive. There are 4 hearts consecutive. So now before deal, we have to re-randomize. Actually, randomize uniformly on the 52 cards. Now there are 52 factorial many choice. 52 factorial many possibilities. Now each must be 1 by 52 factorial. But how many times we have to shuffle? There are 2 types of shuffle we know. One shuffle is just not a just a easy shuffle. Is a it's not actually shuffle. The shuffle is actually by 2 hands, 2 hand shuffle by finger, thumb actually by thumb. Now, if I shuffle 7 times, then it will be uniform over all this pattern, all this 52 factorials. Still, there is question: why is it really uniform? No, actually not really uniform, but it's very close to uniform. Very close to uniform, because after 4 or 7 shuffle, the 52 factorial is very large number. So after 7 shuffle, we can't expect that this will be all possibilities there. So, but it's very close. So some are maybe probability 0, but some not much probability. Okay, it is not 1 by 52 factorial. If it is 1 by 50 factorial each, and some are 0, then we can say, okay, these are really random actually. So how do you prove it, or how do you what is the concept behind that? Is the Markov chain. It's Markov chain. So basically our initial starting, that before the shuffle there is a initial phase, and that is a initial distribution is not random. Basically it's not uniform, obviously not uniform. There is some patterns are there in there. So uniform starting say it is x0, say for example it is a 1 7 9 49 with very high probability. High probability is say 00005 is also high probability. If it's the probability 00005, then also high, because actual each must be 1 by 52 factorial is very low. So if compare with 1 by 52 factorial, this 0.00005 is very high probability. Now we shuffle, and after shuffling, after one shuffle, say the distribution say x1, then it is x2, x7. Now this is a Markov chain. Clearly it is a Markov chain, because if you know xn, to find xn plus 1, no need of knowing xn minus 1, right? Because if you know xn, so what is before that, no need. So what is present is actually the past. Future depends on the present only, not the past, because now it is this position is this. So before one deal, what was the position, that is not important. So after one shuffle, what will be the probability of what is the distribution? That depends only on the last final the present state. So that's why the Markov chain. Now, since the Markov chain, and we'll discuss that. We'll discuss there is a maybe there may exist a distribution such that after a long run, after n tends to infinity, this distribution of xn converts to a distribution. That is called, if it is converged, under some condition it will converge, and this is called stationary distribution. And what is stationary distribution? Basically, stationary distribution mainly, if you start with stationary distribution, is such a distribution. If you start with the stationary distribution, then all the Markov random variables on the Markov chain have the same distribution. That is the idea of stationary distribution. So once this distribution we achieve this distribution, they will never change. So once this distribution achieved, if it not achieved, it is tends to achieve actually. If it is achieved, then after that the distribution will be same. If xn is that stationary distribution, xn has a stationary distribution, then xn plus 1, xn plus 2 all have stationary distribution. That is the idea of stationary distribution. And it can be shown by using Markov chain property that in some probability calculation that after 7 shuffle, this cards are the distribution of the 52 cards are more likely to be is very close to approximately very close to the stationary distribution. So the stationary distribution actually we can prove that the stationary distribution is uniform. A uniform distribution is a stationary distribution for this type of this problem for shuffling of 52 cards. So this is the idea and concept of stationary distribution. It is very common and popular example with 52 cards, shuffling of 52 cards. So we discuss on this, and stationary distribution by its formal definition is the stationary distribution is such a distribution pi x such that if we go one step further, so if I go one step further, the distribution is just summation over pi x p x y from x to y. It starts from x, so it is pi x. It goes to y, so it is p probability of x to not probability, it's a transition function. P x y is starting from x. It's actually x n plus 1 is equal to y given xn is equal to x, and sum over all x you will get the probability of y, and that will be same as this is actually the next step probability, and that will be the same as the previous probability, the initial probability pi y. Then it is called stationary distribution. So if you start with stationary distribution, is ever there. So by matrix notation, pi p is equal to pi, and if you solve this, if you have this transition function, a transition matrix, if you know the p, then you can solve this equation and you can find what is pi, what is the stationary distribution. Now, what is steady state? Steady state stationary distribution is suppose there is stationary distribution. Steady state distribution must be a stationary distribution, but there is an extra property. What is the extra property? That transition function itself goes to the stationary distribution. So it means what happen that there exists a stationary distribution. That means what is the meaning of that? That means if you start with that distribution, there ever this Markov chain in that distribution. If gx0 has a stationary distribution, then x1, x2, xn, all the xn have the same stationary distribution. That distribution, which is called stationary distribution. But it may so happen that there is a stationary distribution, but if we not in the start with the if we not start with the stationary distribution, say another distribution pi 1, then it's not converts to the stationary distribution. Mainly so happen. Then stationary distribution exists, but is not the steady state. What is the meaning of steady state? Steady state means if stationary distribution exists. Not only that, if you start from anywhere, any distribution, this reach to the stationary distribution in limiting sense. In the case of the example of this 52 shuffling of 52 cards. So it's not only the important that stationary distribution exists, it's also important that it is a steady state stationary distribution. Then we can say any starting from anything after some for large n, it's actually close to the stationary distribution. Now there are several questions when the stationary distribution exists. Number one, if it is does not exist, okay. If it exists, is this steady state? Number one. Number two, number three is the stationary distribution unique? Okay, if it is not, if it is unique, then is this stationary steady state? What is the condition if it will be a steady state distribution? Next, okay, stationary distribution is exists and is not unique. Say, so there are 10 stationary distribution. Is there stationary steady state distribution exists, or is it exists for some other from 5 distribution, 5 stationary distribution? There are 10 stationary distribution different, and 5 are steady state, maybe, or 5 are not. Is such a thing happen or not? Or there is a unique steady? If the steady state distribution exists, is this unique? There are several questions are there. But in the for 52 cards, shuffling of 52 cards, there is a unique stationary distribution, and this is a steady state distribution, unique. We can prove that, not proved in the previous class. Now we give an example of stationary distribution. We have a this three state space with three elements 0, 1, 2, and we have this graph representation of the transition functions. 0 to 0 is 1/3, 0 to 1 is 1/3, 0 to 2 is 1/3, and so on and so, and so forth. This transition matrix is 1/3, 1/3, 1/3, 1/4, 1/2, 1/4, 1/6, 1/3, 1/2. Now, how do you find the stationary distribution? The stationary distribution. This was an homework that the stationary distribution is pi 0 is 6 by 25, pi 1 is 2 by 25, and pi 2 is 9 by 25. 2 by 5 and 9 by 25. So if we start with this distribution, is ever there. Now again, this is a question: is this a steady state? If we start with any other distribution, we'll reach there. Now, how do you find if stationary distribution? The another question is, if stationary distribution exists, how do you find the stationary distribution? This is very easy. You have to solve this equation. What are the equations? The equation is clear here. What are the equations? Equations are, it is pi is say pi 1, pi 2, pi 1, it is pi 1, pi 2, pi 3 with this matrix 1/3, 1/3, 1/3, 1/4. Oh, there is a mistake. This is not pi p equal to pi, right? Is the pi p equal to pi, or yes, pi p equal to pi. It can't be p because it is 3 cross 1 with 3 cross 3, so it will be 3 cross 1. One by 4, 1/6, 1/3, half, and that equal to pi. Oh, pi 0 actually, 0, 1, 2 is not 1, pi 0, so 0, 1, 2, so pi 0, pi 1, pi 0, pi 1. So this is the equation. So what are the equations? Three equations are there. So 1/3 pi 0, oh, I says it is say pi 0, plus 1/4 pi 1, oh, it is pi 1, then 1/6 pi 2 is equal to pi 0. Number one equation, equation number 1. Equation number 2, 1/3 pi 0 plus half pi 1 plus 1/4 pi 2 is equal to pi 1. Question number 2. Once then 1/3. No, sorry. This is 1/3, 1/4, 1/6, 1/3, half, 1/3, 1/3, half, 1/3, and then 1/3, 1/4, right? And then half pi. Let's just check this. Is it correct? So if you start from pi 0, 0 from the 0, you can go to the 0 with probability 1/3, right? If you start from 1, you go to the probability, you go to the start from 1, you reach at 0 with probability 1/4, right? And if you start, so 1/4 into pi 1, if you start from 2, that is the distribution probability is pi 2, you reach at 0 with 1/6 probability. So sum of this is this. Okay, this is correct. So you have to solve this. Now question, this system linear equation of 3 variable and 3 unknown, 3 equations, is this distribution solution exist? Number one, consistent, or is it unique, or is it infinite? Now, what is the solution exist? Now, so we just take this side actually. So actually, this in the matrix notation, it will be you can take the transpose actually. If you take the transpose, then okay, you can just think like that. This minus 1 by 4, take the transpose. If you take the transpose, then this pi row vector, pi will be the column vector pi. We actually are familiar with the to write the in column sense. This half minus 1. So if we take pi 1 in the left side, so half minus 1 pi 1, 1 by 3. So 1/3, 1/4, half minus 1. So we write this side, okay, pi 0, pi 1, pi 2, and 0, 0, 0. Right? This is the thing. So this is a system of homogeneous equation. This basically is pi p transpose minus identity into pi equal to 0. This is the equation. 0 means the 0 not 0, 0, 0, 0 vector, column vector 0. Now you can write also in the row sense. Then it is p minus I. Same thing. Same equation. Now question whether this system of linear equation has homogeneous system of linear equation has solution or not. Yes, it is always a solution because it is homogeneous. So pi 0 equal to 0, pi 1 equal to 0, pi 2 equal to 0. But it can't be a solution. Why? Because pi 1, pi 0, pi 1, pi 2 all cannot be 0 because the sum is 1. There is one more equation is this. Because there are probability, there PMF, sum must be 1. So this system as a solution, but this is not satisfy this. Now the question whether it is a unique solution. If it is a unique solution, only 0, 0 is a solution, then there is no solution actually. So the question is whether this system has infinite solution or not. It's a non-trivial solution. There exists a non-trivial solution or not. Now non-trivial solution exists. We know the determinant is 0. If the determinant is non-zero, then this is only 0, 0 is the solution. A determinant is not 0 is singular matrix that p minus I or p transpose minus I, same thing. It's just p minus I transpose is actually p transpose minus I because I transpose is just I. So if this determinant is 0, then it is an infinite solution. Now obviously this determinant is 0 because if we add this all columns or rows now for p minus I, if we add all columns, or for p transpose minus I, this matrix, the last matrix, then if we add the all rows, this will only 0, 0, 0. Because just 1/3 minus 1, 1/3, 1/3. If you add this 0, 0, 0, 0. 1/4 half minus 1, 1/4. If we add this 0, 0, 0. Again 1 by 6, 1 by 3, half minus 1. If we add this, should be 0. Because we know this row sum is 0. This matrix, the P matrix, the row sum is 0. Now it is P transpose. So columns the sum of the three elements in a column is sorry, it is 1. So sum of the three element of a row of a column is 1 here. Now you just take the minus 1. That means what? That means the sum must be 0. So this is obviously is a non-singular a singular matrix. This singular matrix, right? So determinant of p minus I is 0. Clear? Because the sum of three elements of row in P is just 1. So that's why it is determinant is 0. So that means the infinite solution is there. Now once there is the infinite solution, what happens? Once there is infinite solution, now we know that there is a solution other than 0, 0, 0. So take there is a solution. Say solution is say C0, C1, C2 is a solution. C0, C0. This is not pi. This is actually pi transpose. Remember, this is a pi transpose. So pi is say C0, C1, C2 is a solution. It's a solution. Say this system is a star, solution of star. Now what happened? Now clearly If C0, C1, C2 is a solution, then we know this implies that some lambda into pi, which is actually, say it is says pi dash, so lambda C0, lambda C1 is also solution. We know this. Because the all set of all solutions forms a vector space, subspace of R3. In general, it is Rn. So since the solutions set of solutions forms a subspace, this lambda C0, lambda C1, lambda C2 also solution. Now since this is also solution, so we can easily find a lambda such that sum of this is 1. We can always find this is 1. So you can always find that, because in that case the lambda will be, now there is a one problem. If C0 plus C1 plus C2 is 0, that is the problem, right? If C0 plus C1 plus C2 is 0, then there is a problem. The C0, C1, C2 may not be all 0, but sum may be 0. So if sum is 0, then the problem. If sum, so assume that is non-zero. So this sum is non-zero. So we have this already the condition. If C0, C1, C2 have such a solution that C0 plus C1 plus C2 is 0, then all the multiples is, if we add, this is again 0. But if it is non-zero, say it is say 2, then we can multiply by half, and then we can go, we can have this some probability, which is sum is add up to 1. So there is a question. So for which value of p this solution, the sum of the solution, the coordinate of the solutions sum is 0 or not. So if it is non-zero, C0 plus C1 plus C2 is non-zero, then we have a some lambda, and for suitable lambda we find a distribution. Now again there is a question whether this stationary distribution is unique or not. Now this is definitely the question of vector space, subspace form. What is actually kernel of this function? We know that matrix is actually linear transformation. So matrix multiplication is a linear transformation. So question about is if you have a linear transformation multiplied by a matrix is actually linear transformation. We know this. Matrix multiplication is a linear transformation. So any AX, X goes to AX is actually linear transformation. So the linear transformation comes from R3 to R3. Now in this case R3 to R3. Here A is just a P transpose minus I. So this T of some column vector, here it is column vector X, is AX. Now we have to find the kernel of this, kernel of T. Kernel of T is actually solution space. Solution space. Kernel of T, if some X belongs to kernel of T, that means what is the meaning of that? That means Tx equal to 0. So AX equal to 0. Null vector. Now question the kernel, what is the dimension of this kernel space? So we need that rank nullity theorem. So we know that kernel of the dimension, the kernel of the transformation is just 3 minus that n minus actually n minus the rank of the matrix. So we have to find the rank of the matrix. Now rank of the matrix cannot be 3 because it is a singular matrix. Since the rank of the matrix cannot be 3. If it is 3, then 3 minus 3 is 0. So it is 0 is the only solution. Then kernel space dimension 0. That means a trivial subspace of the vector space R3. Now since rank is not 3, it may be 0, 1 or 10. 0 is not actually, it's a very trivial case. 0 means is the P matrix is identity. That means that every state 0 goes to 0 with probability 1, 1 goes to 1 with probability 1. So if you start at 0, it's ever there. If you start at 1, so it is not an interesting thing. So we just discussed that case, say null matrix case. Null matrix means just P equal to 0, P equal to identity. That is a trivial thing. So we forget about P, say P not equal to identity. Otherwise not interesting. Its state is not changing then. That means rank is not 0. So rank may be 1 or 2 in this case. So if rank is 2, then kernel of this, the nullity is 1. So kernel is a one-dimensional subspace, and in a one-dimensional subspace you have exactly one vector whose sum is coordinate sum is 1. You have exactly one vector, and this rank is with 1. The rank of the p transpose minus 1 is I is 1. That means nullity is rank is, or nullity is 2. That means two-dimensional subspace, and it's a two-dimensional subspace. You have infinitely many vectors with this unit unit vector, basically not a unit vector. The sum is 1. The coordinate sum is 1 if I have infinite choice of that. So the question is whether the rank is 2 or 1, and in that case what is the rank? In this example you can easily find the rank of this matrix. What is the matrix? The matrix is actually, what is the matrix? Say minus 2 by 3, 1/4, 6, 1 by 6, half, minus half, 1/3, 1/3, 1/4, minus half. So what is the rank? Obviously rank is not 3, rank is not 0 also. So whether it's rank 1 or 2, you can easily find it is rank is 2, because if you take this submatrix, say this submatrix 2 cross 2, and determinant, what is the determinant? Determinant is just 1/3 minus 1 by 8, so it is not 0. So rank is 2. Since rank is 2, nullity is 1 by rank nullity theorem. So dimension of the null space or kernels, this is 1. So there are exactly one vector. There exactly one vector whose the coordinate sum is 1. So that means in that case the stationary distribution is unique, and this unique distribution is just this. What is this? Is already given. This distribution is 6 by 25, 2 by 5, and 9 by 25. If we add this, this will be 1. So you can just put and you can check this satisfies this three equations. You just check one. You just check one. If you add this, what happens? If you is this solution is one, this first one 1/3 into 3, 6 by 3. It is just 2 by 25. It is 2 by 25. Then 1/4 into this is 1 by 10, and then 1/6 into this. So it is 1 by 3 by 50. So if we add up to what? It is 2 means 10, 4, 4 by 50, 5 by 50, 9 by 50, and then 3 by 50, 12 by 50. 12 by 50 is just 6 by 25, right? So you just check one and it's correct. You can easily check the other also. So this is a unique stationary distribution for this Markov chain. This is unique. And to show it is unique or not, you need this rank nullity theorem or the subspace dimension and this kernel nullity and all this type of linear algebra part. Now, what is the basic idea behind the stationary distributions? Say, consider this example actually. Again, what is the example? What is the probability? This is from 0 to 1, it is probability 1/4, 1/3. From 0 to 2, it is 1/3. From 1 to 2, it is 1/4. From 0 to 0, it is 1/3. From 1 to 1, it is half. From 1 to 0, it is 1/4 probability. From 1 to 2, it is 1/3. How? It is 1/3. Oh, sorry, it is 1/4. 1/3 is the other way. From 2 to 1, it is 1/3, right? 1/3, and this is 1 by 6, and here it is half. Now think about this. Say, what is actually the probability means? The 1/3 probability. So say if you have 3 ball in your hand, say zero is say some person is 0 and some person is 1 and some person is 2. There are 3 persons. They are passing their balls to the other. Now if 0 has 3 balls, actually with 1/3 probability she passed the balls. Actually if you say 1 ball, actually so 1 ball with probability 1/3 we pass the ball to the 1, pass the ball to the 2, and 1/3 probability is remain is himself or herself. Now so this type of 1/3 1/3, so we can just simplify these things. Okay, this has 3 ball, so 1 ball passed to the 1 ball passed to the 2, and another ball with the him or herself. Similarly for 1, the person 1, what happened? If you have 4 ball, that person 1 has 4 ball, 1 ball passed to the 0, 1 ball passed to the 2, and 2 ball remain there. Similarly for 2, if there's 6 ball, right, 1 ball passed to the 0, 2 ball passed to the 1, and 3 balls stay there. That the other 3 balls stay there. Actually, it's like an expectation. With probability half, so 3 ball will be there, and 1 ball will pass to the 0, and 2 ball pass to the 1. Now, consider there are 25 balls. Now, the distribution. What is the stationary distribution? The distribution is 25, 6 by 25, 10, and 9. 6, 10, and 9. 6, 10, 9. Okay, now this you have to 1/3 1/4, so you go with more balls. Say you have how many balls then? 300 balls. Say. So you have total 300 balls, and you distribute these 300 balls to 0, 1, and 2 with this probability. This is the initial distribution. This is the distribution of the. So how many ball the 0 will get? 0 will get. It is just 6 out of 25. That means 72 balls, right? 72 balls with 0, right? Say 24 to another 72 balls. How many balls with 1? This is 12 and 120 ball with 1. And how many balls with this 2? It is just say 36, 36, 108, no? 108. Right. So total 300 balls. Now after next step, what happened? This 72 balls, 0. How many ball pass to the 1? Pass to the how many ball? So 1/3 of the total ball. That means it is 24. 24 pass to the to this, and 24 there, right? Now for 120, how many ball will go to the this 0? This 30 ball, and how many ball with himself? 60, and how many balls pass to the 2? It is 30, right? For 2, 108 many balls, so there are 54 balls will be there. 1/3 and then 1/6. 1/3 is, what is the 1/3 of that? Is it 36? 36 ball go there, and 18, right? 18 ball, right? Now, how many ball after that step? How many ball with 0 with 0 have how many balls? So 24 there already. 30 came from that 1, and 18 came from 2. So what is the total sum? 72. So as many as ball before the step, before this transition. that previous distribution. Now what happened for 1? 60 ball there, 24 came from them, 36. 36 plus 24 plus 60 is 120 again, and it must be 1080. 2 match, then third must match. So that is what this is the idea of stationary distribution. If you start with that stationary part, 72, 120, 108, and after this transition thing, you will have the same thing with all these parts of the same balls. That means same distribution. If you again one more step, again same thing, again same thing. This is the basic idea behind the stationary distribution. So if I ask you that, okay, if I ask the 0% that you just pass your 1/3 of your balls to the 1 and remain yourself with 1/3 and repass 1/3 with the 2, and I ask person 2 say that yourself with half of the ball you stay yourself, and 1/4 of the ball you pass to the 0 and 1/4 of the pass to the 2, and if I ask person 2 to 1/2 of the ball with yourself and 1/4, 1/6 to the 0, 1 and 0, and then if you start with this ball 72, 120 and 108, this number will not change. Now the question is not to start with 72, 120, 108, so it will start with 100, 100, 100. Uniform distribution. Now question is, if it's 100, 100, 100, then it's pass the 0 pass 1/3 of the 100. 1/3 of the 100, say 33.33 and 1/3. Actually, it's a probability, so its fraction is allowed actually. 33 and 1/3 is yourself with the 0 itself, and then 1/3 of the ball is passing to the 2, and again for 1 and 2. Now this distribution will be changed. Not 100 will not be there. Say 110 1/3 and 199 and 2/3, something like that, or 98 1/3, something like that. And again do the same step, 1/3, 1/3, 1/3. If it is steady state distribution, what happened? It actually, after some time at times or a long while of n, actually 0 will have 72, 1 will have 120, and 2 will be have 108 many balls, roughly. For n tends to infinity, it will be exactly, and for say n equal to say 100, after 100 step, it will be say for 0 it is say 72.309, something like that. It is 120.10015, something like that, and for 2 it is 107.009.9835, something like that. Very close to this number. That is actually if it is steady state. If it is steady state. If you start with any other ball with 1, 2, 3, 0, 1, 2, after a long run, after large value of n, actually this will be this number of ball with these 3 fellows will be very it's like a constant after long value of large value of n. It changed, slightly changed, because if it is 72, 102, 108, then it will be exactly that. If it is not that, say 72.05, 120.05 and 107.9, then it will slightly change and change to the actual number towards the stationary distribution. This is the basic idea of the stationary distribution. So we can find some more stationary distribution, something like for unfresh chain. For unfresh chain, what is the equation? This equation is now, it is slightly complicated. Unfresh chain has d plus 1 many state. So equation like that, pi 0, pi 1, dot, pi d with transition matrix P. We know that what is the transition matrix for the unfresh chain, and with sum equal to pi d. So we know what is the transition P. We know the P. So from that we can find this all this probability, all this equation. The first equation is that. The second equation will be what is the second equation? On pi 0 plus pi 2 by d. You know what is the transition matrix for this unfaced chain. You have this list, you know this. P is actually 0, 1, 0, 0, 0, 0, 0. Start from 0, it should go to 1. If you start from 1, then it may go to 0 or may go to 2. If 1 less or with 1 probability 1 by d this and d minus 1 by d. Then 0, 0, 0. Then it is 0, 1 by d, 0, d minus 1 by d. It is d or 1 minus d or 2. It is 2 by d, right? Right, 2 by d. 2 by d, d minus 2. Da, 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 da. Last one is 0, 0, 0, 0, 0, 1, 0. So this is the equation. And if we write this all this equation, is it 2 by d or 1 by d? For unfaced chain. Next one, it is 2 by d, sorry. Right? Yes. For unfaced chain, it is next one is 2 by d, right? 2 by d. So you have the other equation also something like that. What is this? This is 0. 0, then it is for the first one. What is this? For the this is right. The first one is okay. Then this must be. Is this okay? It come back to the 0 with 1 by d probability, and to the to 2 with 1 d minus 1 by d. That means equation is what is the equation? Equation is then no, this is not correct. This is d. This is d minus 1, right? Right. Similar, you have this other equation and you have to solve this. This will be slightly complicated. It is not so easy. The solution of this. Okay, next will be next equation will be pi 1 with 2, then 2 by d plus d minus 2 pi 3 by d is equal to pi 2. So for a large number of stage, this solution will be complicated. Rather, it may not be possible by hand. So you need some software to solve this equation. And there's several software out there. In R also there is a code to find solution, and you know how to find the system linear equation solution for infinite solution. So for better, if to find the infinite solution is exist. So if infinite solution, what will be the idea? Solution is always exist because 0, 0, 0. But you need an extra condition. What is the extra condition? You need that condition. Sum of all this must be 1. One more extra thing is normalizing factor, normalizing condition. Now to find some how to find some infinite solution thing, system linear equation with infinite solution. The basic idea is the more important. Basic, not a basic. It is actually the easiest way to do this is find the echelon form of this matrix, row reduced echelon form, and once you have the row reduced echelon form, you will get what are the free variables and what are the dependent variables. You can, if it is echelon form, you have some, say out of say 10 variable, you will get say 8 are free variable there, and the rest 2 are can be written in terms of the other 8 variables. So you can take any, you have a choice, any choice of your 8 variables, and the rest 2 are just depends on that. If you go to the row reduced echelon form of the matrix, this corresponding coefficient matrix, you will get this. And in R or in C, there is just one command is there. You just write the matrix and you just echelon something like that, echelon A. This C will give you the row reduced echelon matrix. And once you have a row reduced echelon matrix, just finding row reduced echelon matrix is tough by hand, so you need software. So using software, you just using C, you can find the row reduced echelon form of the matrix, and then you can find by your hand. Once you have a row reduced echelon form of the matrix, then finding solution is very easy. So you need all this row reduced form echelon matrix, row reduced thing or echelon part of this, that all this of treatment of with linear algebra. So you need this. It's not a by hand. It is not easy. It is not actually impossible to solve this basically. Next to impossible. Now we have this stationary distribution and steady state distribution, and we have two example, and then we will say some other chain is one called gambler ruin chain. This is called gambler's ruin chain. Ruin chain. What is gambler ruin chain? A gambler start gambling with some say rupee, and if you say pay 1 rupee, if you lose, and gain 1 rupee if you win. Now, if a gambler has 0, then it's called absorbing state. You have to end there. The gambler should end there when it is 0. So state or then state space is 0, 1, 2, dot, 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 dot. Now it is this is anything. It may be 1 lakhs, 2 lakhs. If it's not 0, then the game is going on. Once this gambler has 0 rupee, stop. Now, it may be a slightly modified version. What is a modified version? Is gambler decide, okay, if I have a D rupee, I stop. If I have say 100 rupee, I stop. I start with 50 rupee. If I 0, obviously I have to stop. I have to stop. If I have 100 rupee after 51 winning, or maybe if 20 lose and 70 winning, if I take 100 rupee, I stop the game. So two-sided bounded. Now, what is the probability? Obviously, for x greater than or equal to 1, is not for 0, because for 0 it is p0 0 is 0 1. So 0 to 0 is probability is 1. For other than 0, the transition probability, the matrix is transition function is just say q. Q is the losing probability. So then it is y will be x minus 1. With p, it is and 0 as well. So with probability p win, with probability q it is just Bernoulli tells. Bernoulli tells with probability p is win, and with probability q it is lose. So this is the Markov chain. This is actually the transition matrix of the transition function of the Markov chain. And so once you have the transition function, we know what is a Markov chain. The transition function or transition matrix actually characterize all this Markov chain actually characterized by this transition function. Now there is a two-player modification. Again, two-player modification is this: if there are two players, say, if once have say, if then it is for the S dash, it is P00 is 1, again PDD is 1. That means if you have D, that other plus is 0, say. Total sum is say you have 50 rupees and your opponent has say 70 rupees. So D is 120 now. So if you have 120, then you, because the other player has 0 rupee, so game will be stopped there. 2% modified thing. So if you have 50 and other player is 70 rupee, so D is 120 now. If it is 0, then stop. If it's 120, then also stop. So this is called 2% two-player modification of this gambler ruin chain. And the last chain is this same type of slightly generalized. Actually, gambler ruin problem is a birth and death chain. Birth and death. So what is birth and death? There is a slightly generalization. So birth and death chain is start from x, maybe one birth, one death, or maybe no birth, no death. That means your S is just, again, it will be 0. 0, there should not be any other birth, no birth. So these non-negative integers, and this transition function is say qx, It is if y equal to x minus 1, that means is death probability. Rx, it is actually if same thing, and it is px 1 birth and else. Now clear, you see this in the gambler ring problem, this p and q does not depend on x, but obviously this rx, qx, px depends on x, because probability of a birth and probability of a death, obviously it is depends on the size of the population. Size of the population is actually mortality rate. Is mortality and is fertility rate. Yes. Birth rate, crude birth rate and crude death rate. You know this CRD, CDR or something like that in vital statistics. This actually is in the vital statistics. This is Markov chain model. So this depends on x actually, that size of the population. And in all this case, you can easily, not easily, you can actually try to calculate the stationary distribution and some sort of this virus infection or this COVID situation. That some model is there with this birth and death chain. Is there any stationary distribution or not? If there is stationary distribution, that means this will be after that this will be stationary. But obviously, it's not a pure death and birth chain, because there is an external factor is there. External factor means the vaccinations or other say gathering in a festival. This will then Rx, Px will be high then. If the vaccinated, then Qx will be high. Or if there's some medicine, then Qx will be high. So this is actually dynamics called dynamic birth and death chain. Then this actually some working with this Markov chain thing with. It's not actually purely Markov, but Markov chain. But if you can model this with a slightly modified thing, or you can guess something about this, any pandemics, or not only in the pandemic, any other infection or any other virus or bacterial infection thing, you can model this Markov chain thing. The number size of the virus, size number of virus, or number of the size of the populations, or number of infected persons, something like that. Obviously, these are all p plus q is 1. I forget to tell you that it is p plus q is 1, and obviously p and q must be both are positive. And here qx, rx, and px is positive, and px plus rx plus qx is 1. And you know this Gamble ring thing and unfair chain is a special case of birth and death chain. If you take rx equal to 0 and qx equal to q and px equal to p, is without not depends on x, and rx equal to 0, then it is just a Gamble ring problem. And again, you can modify this birth and death chain with this state space. Its modification is once it is reached d, it stop there, no further birth, or maybe their death, not but no birth. So these are the several versions of this birth and death chain, and this is up to this we complete the stationary distribution. Next day we'll start with the heating time and other distributions and classification of states, something recurring state, transitions, transient state, and this actually needs some very sound knowledge of linear algebra, and as well as this distribution theory, and the actually convergent of distribution theory, this CLT or weak law large number, some probability thing. So that's for